Let's do one more partial fractions example today to start. That's a bit trickier. I'm going to make the function we integrate be a rational function with a cubic denominator. Yikes. X cubed minus x squared plus x minus 1. Is this integral possible to do? Well, I wouldn't be doing it if it weren't possible. It is. It is challenging. The first thing that should come into your mind is, boy, I hope I can factor that cubic. Because if I can factor it, then maybe I can use partial fractions. Now, factoring cubics in general is difficult. You could graph it to help you estimate roots. This particular one turns out to be nice. If you happen to notice, if you replace x with 1, you will get 0 on the bottom. 1 minus 1 plus 1 minus 1 is 0. In other words, 1 is a root of that polynomial. X minus 1 is a factor of the cubic in the bottom. So if I do long division of polynomials, dividing x minus 1 into the bottom of this fraction, I should get a remainder of 0. That should happen, since 1 is a root of that. I have to multiply x by x squared to get x cubed. So I put an x squared up there. Then I multiply x squared times each term and put it down here, giving me x cubed minus x squared. Then I subtract. Those two terms cancel. What's left is x minus 1, which matches what we're dividing into this thing by. I have to multiply x minus 1 times 1 to get x minus 1. Subtract, and yes, I do get a remainder of 0. X squared minus 1 is the quotient. 0 is the remainder. If x squared minus 1 were something that I could factor easily, then I would continue factoring. However, x squared plus 1 is not factorable over the real numbers. Its two roots are plus or minus I, the imaginary units. So because of that, we don't try to factor it. Instead, we write the function like this. And we try to use partial fractions right away. We take the function we're integrating, 1 over x minus 1 times x squared plus 1, and we try to break it apart into two pieces. If, by the way, the denominator were a product of 3 linear terms, like maybe x minus 1 times x plus 2 times x minus 7 or something, you'd want to break the fraction into 3 different fractions with numerators a, b, and c. But here we have 2 factors, and so we use 2 fractions, one of which does have a denominator of x minus 1 and the other x squared plus 1. However, it's a bit trickier here because when you have a quadratic irreducible here, like we do, you need to allow for an x term in the numerator. You need to allow for a linear function of x, Bx+C. So what this means is there are still 3 unknown constants to solve for. But just keep trudging ahead. Multiply both sides of this by the common denominator of x minus 1 times x squared plus 1, giving you complete cancellation on the left, partial cancellation on the right. The x minus 1s cancel by the a, leaving x squared plus 1. And by the Bx+C, the x squared plus 1 cancels, leaving x minus 1. By the way, most of these examples I've been doing 1 or some other constant has been in the numerator. It didn't have to be a 1. It could have been an x, for example. And then I would have had an x there and an x there. And when I substitute values of x, I have to take that into account. However, this is a bit harder, not only because you have 3 unknowns, a, b, and c, but also because there's only one simple number you can plug into the right side to give you 0 in one of these terms. It's if x is 1. Yeah, I mean, you could try x is plus or minus I over there, the imaginary unit, but then we'd have an I over there as well. Theoretically, it's possible to do with plus or minus I, but I think we want to avoid that. If we plug in x equals 1, we get 1 equals a times 1 squared plus 1 is 2. And then if I plug in 1 over here on the right, I get a 0, plugging in right there. So in other words, 1 equals 2a. This implies a is 1/2. A is easy to solve for. B and C are a bit trickier, but still doable. It's still worthwhile to plug in other values of x that are simpler or fairly simple numbers, like 0, for example. Even though it doesn't make anything on the right side equal to 0, it still is worth plugging in. Plug in 0 there, you get 1. Get a times 1. Plug in 0 over on the right here. The b will go away. B times 0 is 0, but the c will still be there. And it'll get multiplied by 0 minus 1, which is -1. Don't fret. We already know a is 1/2. Plug it in there. This is now a fairly simple equation. We can solve for c. Add c to both sides. Subtract 1 from both sides. If you do that, you get c is -1/2. What other value of x should I pick? I mean, I could pick -1 maybe, or maybe it's simpler to pick 2 because 2 minus 1 is 1. Try to make things as simple as possible. If x is 2, 2 squared plus 1 is 5. And then over here, plug in x equals 2 right there. I get 2b plus c, right? 2b plus c. I replace the x with 2 right there. Replace this x with 2. 2 minus 1 is 1. Now substitute once again, a equals 1/2 into here, and c equals -1/2 into there. And we get 5/2 plus, in parentheses, 2b minus 1/2. I can get rid of those parentheses and then do 5/2 minus 1/2, which is 4/2 or 2. And then solve for b. 2b will be 1 minus 2 is -1, and therefore b is also -1/2, just like c is. There are my values of a, c, and b. 1/2, -1/2, and -1/2. Go back up here and plug them all in and integrate. Well, okay, let's be a little careful. Plug them back in here. The function we're trying to integrate is going to be, a was 1/2, 1/2 over x minus 1, plus the b and c were both -1/2. -1/2 x minus 1/2 over x squared plus 1. Now remember what our goal is. We're trying to integrate this function. It's equal to this. Integrating that is easy. Think with me here. That would be 1/2 natural log of the absolute value of x minus 1. Integrating this, a little harder looking, but if w were x squared plus 1, dw would be almost up there. Not quite. If w were x squared plus 1, dw would be 2x dx, which is, I mean, there's an x in there. There's this extra constant. It's going to be worthwhile to break that fraction into more pieces. I'm no longer doing partial fractions, but this is still helpful. Like that. And that's what I want to integrate. So the original integral, I'll write the original form of it as a cubic here in the bottom, is equal to integrating all this which will give 1/2 ln absolute value of x minus 1. Be careful with this one. If I were going to integrate that and be extra careful, I'd want to let w be x squared plus 1. dw would be 2x dx. X dx would be 1/2 dw. That's what x dx would get replaced with, and 2 1/2 would give a 1/4. So I get minus 1/4 ln of w, which is ln of the absolute value of w is ln of the absolute value of x squared plus 1. Though absolute values are not really necessary there because x squared plus 1 is positive when x is a real number. Just a second here. Finally, integrating this one's going to be minus 1/2 ln, or excuse me, inverse tangent of x plus c. Let's see if Mathematica produces the same answer. Maybe even check our partial fractions. That can be done as well. We can use a built-in command called apart to essentially do partial fractions for us. The original function, 1 over x cubed minus x squared plus x minus 1. Yes, the coefficients where a was 1/2. There's the 1/2 right there. There's a 2 right there. B and C were both negative 1/2. You can see the negative signs and the 2 down here. That's right. Let's check the integral. Yes, it looks good. Mathematica doesn't bother with the absolute value signs, doesn't bother with the plus C. You should. And remember, log in Mathematica means natural log.